All right, Charlie Stanier here again with online mini lecture 11, continuing to get into particles. So in a reminder, please read chapter 8 of Seinfeld and Pandas about particles and particle size distributions. To review, we introduced particles, sometimes we call them aerosols or aerosol particles, which are solid and liquids in sizes of diameters of 1 nanometer to about 10 microns suspended in air. We talked about the choices that you have to make when you're representing a particle population. You have to choose your variables of interest. Size of particles is almost always going to be one of the variables of interest, but shape, chemistry, reactivity, optical properties, whether there's any living, DNA or other biological materials in there. It can be all kinds of variables of interest. When you describe the size distribution, you have some choices to make about normalization and axis choices. We presented typical sizes of some particles, human hair, coarse particles, fine particles, some virus particles like coronavirus that are very on our minds a lot right now. And we started an example with a size distribution. I just wanted to motivate why it's important to be able to understand these size distributions. So I'm going to jump ahead a little bit just to show you an example. Right, so this is the population of particles described in terms of their size only, or size and concentration, measured from people speaking. So when you speak, you emit aerosols. If you're infected with an infectious disease, a respiratory disease, then those aerosol particles may be loaded with the infectious agent. So my point is, you need to be able to understand what the heck this means. So we've got an x-axis that is apparently the base 10 diameter, so 100 nanometers, 1 micron, 10 microns. And we have a y-axis, which is, I don't know, what is that? That's complicated. D, Cn, D log, D inverse cubic centimeters. So if I were to, if I put, this is sufficient information to answer a question like, if I have a room 5 meters by 5 meters by 3 meters in size with 10 people all speaking in it, how many particles should be in that room emitted from speaking, right? And then what size are those particles? Let's say only one of them is speaking and the rest of them are just breathing. How different is this population of particles from this population? Let's say one of them is coughing, right? How different is this one from the other two? And so on and so forth. So that's why we need to understand how to go from measurements to these distribution functions and back. Which brings me to our example. So we had 12 size bins. And we want to explore some options for how we could represent this as a distribution function. Well, the easiest thing when you see something like this is to say, let's make a histogram, right? We've got some binning to do on the x-axis, and then we just make the height of the histogram like this. the highest one is going to be 200. And this is, there's another 200. So guess what? We did that. It's, you know, the problem with this is this bin is really, really narrow, right? We need to go all the way out to 10 microns, but this bin is like, you know, 1/1000th. So it's very, very narrow. And so if there's a little spike here that goes up to 200, but you can't see it unless you make an inset that focuses in on that initial size bin. So there's the 100 that goes here from 0.01 to 10 microns, and then here's 10 to 20 microns at 200. So in terms of the choices that we had to make, we didn't do any normalization. This is just a straight histogram. We chose a linear axis, right? And so you broke two of my recommendations, right? I said you should normalize the y-axis because, you know, we can say, well, what if we take this bin right here and split it into two? Instead of, so this was 160 to 320 nanometers. And there were 200 particles in that bin. But let's say we split it into 160 to 250, 250 to 320, and they each had 100 in them because the total was 200. And so all of a sudden, we're changing the shape of the size distribution because we would have two bins, one here and one here. And so that's why we recommend normalization, where you divide the number by the bin width, so that if you change your bin choices, you don't change the shape of the distribution. The other recommendation that this treatment violates is we said we do recommend log spacing in the x-axis, so that you don't need to have an inset to see the details that are often present in the very smallest sizes. So that was 28. So this is page 28 in my page numbering. So now let's try normalization. And so bin 1 was from 0.001 to 0.01 microns. And that bin had 100 particles per cubic centimeter of air. The change in width is, you know, the right side of the bin minus the left, so that's 0.009. And then the normalized concentration, the number of particles divided by the bin width, is that divided by that, which is 11111, and then I divide the units too. So this is number of particles per cubic centimeter per micron of bin width, which is an odd unit, but it's the normalized unit. Bin 2 ran from 10 nanometers to 20 nanometers, had 200 particles per cubic centimeter. The bin width was 0.01 micron. Then I take that divided by that, I get 20,000 number per cubic centimeter per micron. So if I keep doing this for all 12 bins, and then graph it, you get this. So you can tell they've normalized because it's per micron in the y-axis. Those narrow bins got pushed way up. The wider bins got pulled down. And so now the shape is invariant. We could divide this bin into two, and that would change the number of particles by a factor of 2, but it would change the bin width by a factor of 2, leaving the distribution function height the same. However, we're still not using a log scale, so there's a lot of interesting detail. There's here below 100 microns, but we can't see it, so we have to make this inset figure. So let's fix that. So now let's do all the recommendations. Log axis, and we're not quite at all the recommendations. We're still going to make one mistake. We're going to do a log axis, but we're going to do delta n over delta dp normalization. So the same normalization we did here. So the mistake that we're making is the normalization should match the axis. And the reason for that is if they match, then the total number is proportional to the area under the function. So if I use this normalization, right, that's what I just did. And so basically what I'm saying is here's the linearly normalized distribution function on a linear axis. You say, well, I can't see what I want to see over here, so let's just do a log axis. Leave the normalization the same, but use a base 10 log axis so that we can see this. If you do that, this is what you get. However, you'd like to say, well, when you see something like this, you'd like to say, okay, well, that's 20 nanometers. Below 20 nanometers, we got a lot of area. So there must be a lot more small particles below 20 nanometers than there are large particles above 20 nanometers. And that's the wrong conclusion, because we didn't use this, the normalization isn't the log 10 normalization. So if we do it following all of the recommendations, we get this. So now I've got the log 10 x-axis, and instead of normalizing to the linear bin width, we normalize to the logarithmic bin width. And now you could, the area here is proportional to the number of particles, right? And we can do things like say, well, Below 100 nanometers, it looks like there's about maybe 2/3 as many as there are above 100 nanometers. And that is correct. We can also pretty quickly do some calculations. Let's say we're interested in the particle concentration between 10 nanometers and 100 nanometers. And so what we need is the average function height in that size range. And then we just need to know the difference here on a log 10 basis. So the logarithm of 0.1, right, is -1. Logarithm of that is -2. So the distance between here is 1. It's 1 decade of distance. The average function height, well, the area in here is about the same as the missing area here. So the average function height is about 320. And so the number of particles between 10 nanometers and 100 nanometers is that distance, 1, times the average function height, which is about 320, or there are about 320 particles per cubic centimeter in size range B. Right? And I've repeated this approximate visual integral for size ranges A, B, C, and D, where A has about 100, not about 100, it's exactly 100 because it's at 100 for the whole decade, and it's 1 decade. Then about 320 in size range B, maybe about 450 in size range C, and 100 or so in size range D. If I add those up, I get 970. The actual data that we built this size distribution from had a total of 916 in that size range. So that's an example of the distribution functions. So let's come back to our coronavirus example. I'm going to pull out the coughing one. So now we look at this, we can understand a little bit more what they did. So I don't know what the dotted lines are. We'd have to look in more detail here, but they've got some data, right? They've got a fit of the data, and then these solid lines are some sort of uncertainty range on it. But we've got a mode that's maybe at, so that's 100, 200, 3, 4, 5, 6, about 700 nanometers is the most common size of particles emitted by coughing. And now let's think about what this y-axis is. And it's really dn, well, dCN. So this is condensation nuclei, or cough nuclei. These are the particles. This is the number of, this is a normalized indication of the number of particles. And the normalization has been done on the log 10 basis of diameter. Now, we can't know for a fact that this isn't meant to represent natural log, but it's a good chance because they use base 10 log here, and they're engineers. Lindsay Marr is an engineer, so most engineers, when they write log, they mean the base 10 log. Computer scientists, mathematicians, we don't always know. But an engineer would typically write ln here for a natural log. Okay, so now we can say things like how many particles are there smaller than 1 micron. And so this is 1 decade right here. So delta n, that's our question. How many particles is going to be proportional to the function height, dn d log dp times delta log dp. Well, delta log dp is the base 10 log of 1, which is 0, minus the base 10 log of 0.1, which is negative 1. So that's 1. So that's going to be 1. So now it's what's the average function height in this range. And let's say this comes down to like that. The average function height across this whole range, I don't know, it's sort of like that's the average function height for this part, but that's only 2/3, so that's only 1/3 of the range, so I need to decrease this quite a bit. So we might say something like that. And what I'm saying is the area here is maybe the same as the area here. And if you buy that, then this is the average function height at 0.025. And this has units of particles per cubic centimeter. Okay, so there we have it. So there would be 0.025 number per cubic centimeter. This is probably per cough. And now we get into what's the dilution volume that they're using. So there we got to get into the actual paper and see more. Okay, so now we've talked about some best practices. We've done an example. We did a second example with cough particles. Now we're going to generalize. So distribution functions, or you're going to see them all over the aerosol and atmospheric science literature. You need to get used to them. The nomenclature in our book, N sub n, is normalized by delta dp. So this is the distribution function. And we might say n sub n is a function of dp, right? That's a number distribution function. Its definition is the limit as delta dp goes to 0 of the number of particles in a bin divided by the bin width. And we can also write that as the differential number of particles divided by the differential bin width, dn ddp. So once you have this definition of the number distribution function, then I can multiply by ddp and get dn. And so we say, okay, dn is the number distribution function times the differential bin width. And then if I want to know the number of particles from size 1 to size 2, I have to integrate the distribution function. The integral from dp1 to dp2 of n sub n dt dp. The total number of particles in air is just the integral from size 0 to size infinity of the distribution function times ddp. this is all based on particle number. We could do the same with surface area or volume or mass. And you could say, okay, the surface distribution function as a function of particle size is defined as ds ddp. Or the volume distribution function could be the differential amount of particle volume divided by the differential bin width. But number, surface, and volume of spheres are related, or of any shape. But if you know the shape, you can do the inner conversions between these. So for spheres, surface of a particle, the surface of a bunch of particles is proportional to the number of particles, pi diameter squared, so then the surface distribution function, right, is also proportional to the number distribution function times pi dp squared. Volume for spheres, for a bunch of spheres, is going to be proportional to their number, pi over 6 dp cubed. And so the volume distribution function is proportional to the number distribution function times pi over 6 dp cubed. So this was all normalization based on the linear bin width. You will also find normalization to the base 10, or I'm sorry, the base E, the natural log bin width. And in our book, that nomenclature is given by using E in the distribution function. So this is normalization by delta ln dp. If it's a number distribution function, so we would call this the number distribution function with the natural log bin normalization. Right, and that is going to be dn, the number of particles in a bin, normalized by the change in the natural log of the bin width. And then we can also have the natural log based surface distribution ds over d ln dp d, and then the volume based distribution function dv over d ln dp. Same information content, is just a different normalization. And then we can also do the base 10 log normalization. And this is the most common choice, and this is the choice that Lindsay Marr had shown in that data on the cough size distribution. And in our book, this is given by the degree symbol. And if it's number, then that would be dn over d log base 10 dp. And the 10 often gets left out. And just to be clear, it's like that. So conversions between these, they all have the same information content, so you should be able to convert from one to the other. Let's say you were given a normalized distribution, but it was normalized to the linear size, just the linear sizes. And you want to compare to something else, and you need a base 10 log normalized distribution. Okay, well, this is the definition of the linear distribution function. And this is the definition of the base 10 log normalized distribution. And we've got one thing that's common to both equations, the dn. So we solve for that. Equate them. And solve for, we wanted this in terms of this. So it's going to be proportional to it, and then ddp over d log 10 dp. This is equal to 2.303 times dp n sub n. I'll show you how we get this. So a little bit of calculus review. So we can change bases of logarithms. So the base b logarithm of x is equal to the base b logarithm of c times the base c logarithm of x. So we're going to choose b of 10 and c of Euler's number e, right? And so the base 10 logarithm of x is equal to the base 10 logarithm of e times the base e logarithm of x. E is equal to 2.718, and the base 10 log of E is 0.434. Okay. Showing that the base 10 log normalized distribution function can be calculated from the linear normalized distribution function times that ratio, and that is equal to 2.303 times particle diameter times the linear normalized distribution function. So given this, we can calculate this, which was what we wanted. Then we said, need to show that this is true. So this must equal this. So how can we show that star is equal to star? We had that bit of review that the base b log of x is the base b log of c times the base c log of x, and that can be used to show that the base 10 log of x is equal to the base 10 log of e times the base e log of x. In other words, the base 10 log of particle diameter is equal to 0.434 times the natural log of particle diameter. And then we think about, if I take the derivative with respect to particle size of the natural log of particle size, that's just 1 over particle size. Just like if we said d by dx of ln x is 1 over x. Right, but I can substitute in, because the ln of dp is related to the base 10 log of dp, so d by dp, ddp. So substituting in, solving this for here, substituting in for there, that's going to have 2.303 log 10 dp. It's going to be 1 over dp. Too many d's here, but right, and then we can pull this constant out, so that's 2.303 times d log 10 diameter over ddp is equal to 1 over dp. So we're almost there. If we bring, we're trying to show that that is equal to that. So if we bring dp over to the left and then divide through by both sides by this ratio of differentials, then we get 2.303 dp is equal to ddp d log 10 dp. Right, and we've shown what we needed to show here. So these kind of transformations are, there's examples of them in the book. There's some of the final conversions in the book, but I wanted to show one in detail and emphasize that the key idea in these transformations, right, is here's the definitions of the distribution functions, and they share in common the differential number of particles. And so then by solving for that on both sides, equating them, then we can get the relationship, and then there's usually a little bit of calculus to get these kind of ratios of differentials. So we said the naked virus is about 120 nanometers for coronavirus. Here's for influenza at 100 nanometers. However, the airborne virus is not naked. It's trapped in respiratory fluid. So whether it's coming out in breath, or in a cough, or a sneeze, or while you're speaking, all those are going to be some mix of respiratory fluid and virus. Now, the size of this particle determines two really important things. Its atmospheric lifetime, because of that settling, that strong relationship we said with the gravitational settling velocity and size. And it also determines where in the respiratory system it deposits, so nose, throat, upper section of the lung, deep lung. However, this isn't a constant, right? Because a lot of this is water. And if this enters into a dry environment, it's going to lose water, evaporate, and shrink. And that's shown in Lindsay's next slide here. So in very high relative humidity, it's not going to shrink much. It'll have a fast settling velocity, shrink in 1 minute. From a chemical composition standpoint, you're going to have a lot of water, which is shown by the clear section. And then you're going to have other substances of respiratory fluid, which might be proteins, what else would be in there? Maybe some lipids, and then your viral particle. Under medium relative humidity, it's going to retain some water, but all the things that can't evaporate would be concentrated. And then if it's very dry, then all the water would be thrown off, and I'll be left with just the virus and then some other biomolecules that are trapped in that solid phase. It's going to get a lot smaller, it's going to settle more slowly, and so it's going to be able to distribute more around that indoor environment. How much it evaporates as a function of relative humidity is something we can calculate. The atmospheric humidity controls the final size. That control is a common derivation in aerosol science. It's called the Kohler equation. And my next slide says where in the textbook it is. But the relative humidity, so that's like determined by the weather or the building controls, the HVAC system, how the building is run. The relative humidity is going to be equal to the partial pressure of water over the droplet divided by the saturation pressure, which is just a function of temperature. However, the pressure over the droplet is not just the same as the pressure over pure water. It's got two terms in here that are parts of the Kohler equation. So what's showing here is, let's say a particle was emitted from the body, 100% relative humidity, 10 microns in size. And then depending on the room's relative humidity, it might shrink to 4 microns. The amount of shrinkage can be calculated by this Kohler equation. And the Kohler equation is in chapter 17 of Seinfeld and Pandas. And I bring it up because it's just very relevant with this coronavirus situation. You get it by solving for the equilibrium thermodynamics of a curved droplet composed of dilute salt water, which is basically what these sneeze and cough and breath particles are. There's our relative humidity. I've defined all the droplets. We've got a term here that's called the Kelvin effect, and this is the increase in the vapor pressure over a curved surface relative to a flat surface. And then this is the decrease in vapor pressure due to the presence of a solute. So instead of all the molecules at the surface being water, some of them are going to be dissolved substances that are not evaporating. And so it's going to prevent some of the escape, because not every surface site is available for escape of the volatile substance. And so this is the solute term, this is the Kelvin effect term, and basically if you know the relative humidity, the only unknown here is going to be the particle diameter, right? Because everything else, molar volume of water, the amount of salt or anything that's not water in the droplet, that could be measured as well. And then we've got surface tension of water, saturation temperature of, the saturation pressure at the temperature of the problem. So again, the only unknown is diameter. And if you tell me the relative humidity and the initial size of the droplet and the amount of salt and virus and anything that's not volatile in it, we can calculate its final size, which would determine its final settling velocity, or once it goes into the lung and it's rehumidified and it grows, but we need the same Kohler equation plus some mass transfer kinetics, because that breath is going into the lung quickly and the particle can't grow fast enough to be in equilibrium in the lung. But that's another story, and I'll really stop there.